What happened? What happened to this place? I don't know. For some reason, I lost the two screens. So this was the other. Can you see? I have no idea what happened. Even next time is not there. What are those two? I have no idea what happened. Can you guys see the little one? The little one? Oh, okay. All right. Yeah, we're back. Okay. Now what it means is these two are constant, so your gravity is actually inversely proportional to r squared. Alright, which means more the radius or more the height, your less will be the gravity. Alright. Now I'm trying to do something different here. What I'm trying to do is I'm trying to get the potential energy of the earth. Alright? So how you do the potential energy of the earth is the following. By the way, this problem I used to ask the theoretical, the one that I said theoretical thing. This is one of the theoretical things, okay, that I may ask you. To find the potential energy at any point at a certain height. Meaning the potential energy of an airplane, let me repeat, the potential energy of an airplane flying at 2 kilometers up will not be mgh. Are you following? So the point here is the potential energy will be mgh as long as the gravity between those 2 points are same. If your h is like 2 meter, 5 meter, which is the gravity here and there is same, right? There is not much difference. Make sense? W, G, G always, right? But if the height is significant, like high, then your gravity, will you take that gravity or here gravity? Now you are in problem. Are you following? So that if there is a certain significant height, few kilometers, then you cannot use mgh. Alright? Now what you need to do there is the following. Okay, so this is my tiny little earth. Let me use a separate paper. Potential energy at any point, inside the gravitational field. That's what I call it, okay? Gravitational field. What do you mean by inside the gravitational field? Let's say this is the earth. Alright? This is the earth. Mass of the earth. You have a gravity here, you have the gravity here, you have the gravity, but at a certain point, miles and miles away, there is no gravity. Is that right? So earth can pull back only at a certain height. After that height, there is no gravity at all. So that the body will not come to the earth. Does it make sense? So at that point, we call it like outside the gravitational field. Alright? Outside the gravitational area. Alright? So inside the gravitational field, somewhere here. Alright, somewhere here. at a distance, I call it at a distance r from the center of the earth. Is given by the amount of work done by, I'm writing in the own language, by bringing the body from, I call it infinity. Infinity means outside the gravitational field, okay? Let's say infinity is, it's somewhere here. This is the gravitational field. Outside this field there is no gravity. So this one is my infinity. Alright? From infinity to that point. To that point means this point. Let's say I want to find the potential, gravitational potential U1 at point 1. At point A, let's say I want to find UA. Alright, at this point. So if you want to find UA at this point, what you want to do is, let me repeat, the potential is nothing but small work done is force times d, let me say this is small displacement dy, which is at a distance r. Are you following? Or at a distance, let's say y distance from the center of the earth. Alright? So I do f times dy. Now if I need the total work done, it's something like this. Oops, integration, right? Alright, integration with respect to dy. So integration of f dy. Are you following? So I want it at a distance r. No, let me do it this way. If I take this r, let me do it this r. I want to find u at r. I find it u at r. Okay, r means at a distance r from the center. This will be easier. So I want to find the potential at this point, but bringing a body from infinity to this point, I'm going down, I'm trying to get the total work done on bringing this from infinity to here. On the way, I have a small displacement dy at a distance of y. Are you following? So if I want a small dw on the way, will be force times dy. This is only from here to here. Is that clear? Right? So now, what is my force in this one? The force is G M, right? Right? M. M is the mass of this guy. M. Another M is my mass of the earth. Alright? Divided by, what is my distance? It's y. Y squared. This is my force. And then I have dy. I need to integrate it from where? From infinity to that point. From infinity to that point. If you understand this one line, you are done. So here, let me repeat once again. I have a point something called infinity, and I have a point something called r. I want to find the potential at point r. Okay? What I do, I take a certain a point somewhere in between, where the small displacement at a distance y, the small displacement is dy. So my small work done will be force times dy. So now what I need is, I need the whole work done from here to there, from up to here. So I need to do this f dy, I need to do the integration from infinity to this point. So this is what I do. Make sense? So this is simple. This is constant, this is constant, this is constant. So remaining is simple. So this guy comes out, this guy comes out, mass of the earth also comes out. All I have is integration y2, I push it up, I call it y minus 2, is that right? And then I call it dy, and I have infinity, I have r. If you do this integration, I hope you guys know how to do the integration. This will be what? Y to the power minus 2 plus 1. So it will be minus 2 plus 1 divided by minus 2 plus 1. Is that the formula? And then I have to replace it what? From infinity to r. Very good. So this will be, excuse me, this will be minus 2 plus 1 will be minus 1, right? So I put it here minus G M N E, and then this will be y to the power minus 1, right? So which is 1 over y. Can I write it this way?
We can see.
Oops. So y to the power minus 1, minus 1 goes bottom, and this minus comes front. Is that okay? So now what happens is, now all I have to do is I have to put the upper limit minus lower limit, right? Minus G M N E 1 over d plus y by r minus 1 over y to infinity. What is 1 over infinity? 0. Very good. So this is minus G M N E divided by r. So this is the potential energy, or I call it U at r. Alright. The potential energy at r is given by minus G M N E by r. Alright. So once I ask this question, okay, to solve it, 25 points. Some of the students just memorize. They have no clue how to do it. Just memorize like step by step. And I knew it. But it's not necessary. Yes. So the point here is, okay, the point here is, let me repeat the setup once again. The point here is, well, if you know calculus, this is very basic of the calculus, or integration. And if you don't know calculus, then you know it is like a huge thing. So if you have the earth, let me do the setup here once again, okay? If you have the earth here, which is mass of the earth E, I'm using my red pen, I don't know if you can see it, but okay. And I want the potential energy at this point, which is at a distance r, which is not the radius of the earth, okay? This is r. This is r. I want the potential energy at this point. So what I want is, I need to, here's the thing, total work done by bringing from infinity to that point, to the r. So I need to have infinity. So this is my gravitational region, the maximum. At this point, your potential energy at infinity will be 0. Of course, if there is no gravity, the potential energy will be 0, right? So from here, I start bringing it down, isn't it? So when you bring it down, what happens is, let's say at a certain distance, I call it y. At a certain distance at y, I have a small displacement called dy. Alright? So that my small dw will be force times dy. Force at y times dy. So basically, this is force at y. Alright? Force at y. And then dy. So the question here is, my small dw will be force of y at dy. So all I have to do is just do small work done is force of y, force at point y and dy. The force, gravitational force will be Gmm by r square. This we know it very well. But since it is at a distance y, so r square is replaced by y square. Are you following? And then your force of y will be this guy, and dy, all you do is integrate from infinity to there. And of course the answer will be negative. The reason is, if you do a work done from bringing it infinity, from up to low, right? You do the negative work, because earth will do it for you. You don't have to do it. Are you following? Does it make sense? So the earth will do like negative work. If you take this from here to here it will be positive, because yes, now you are working, you are really using your force against the gravity. Are you following? Then your work is positive. But if you're going down, then of course the work is negative. Does it make sense? Make sense? So that's why your answer will be negative. This is the gravitational potential energy. This is called gravitational potential energy. Sometimes there is a term called gravitational potential. If you say gravitational potential only, no energy, in that case it means you don't have a mass, you have only it's only a point. Gravitational potential means potential at a point without mass. So it means gravitational potential will be, I just write here, let me write it here. So the gravitational potential is what? Gravitational potential is what? It's simply minus, you replace this guy with 1. So it's only G(n)(E) by R, only R. Now you know we talk about so many things. Now let me do one thing which is also called escape velocity. Okay, also called escape. What is escape velocity? What is my escape velocity? Just by the word escape means what? Yeah, going away. Meaning, if you throw this pen, alright? If you throw this pen up, it doesn't come back. Alright? Meaning, it reaches the outside the gravitational field. Alright? You have to throw it in such a speed. So if you throw it with that speed, that velocity, the object will not come back to the earth. The velocity is called escape velocity. So what it means is, how will you calculate escape velocity using the energy method? By the way, before doing that, I think Professor Chapaka, did he do one problem with getting the velocity at any point using energy method? He did the Arduino machine, right? Right, with the energy method. You know what? Let me hold. I'll hold it here. This one. I'll hold it here. I'll do one simple thing. Going back to the one which is dropping from here. Alright? Dropping from here. If I go back the same thing. If the mass is dropped from a certain height, alright, at a distance, let's say 5 meters. Are you following? At a distance at 5 meters. Let me repeat. If a body is dropped a distance of 5 meters, what will be its velocity? Which is very simple, isn't it? It is very simple. Meaning what? How you do this? Your v0 equals to 0, right? Isn't it? Your y equals to 5, your acceleration is 9.8, you get the velocity. The formula for velocity is v square equals to v0 square plus 2ay. Is that right? So v0 is 0 plus 2 times a is what? 9.8, y is your 5. So 5 times this will be whatever. So you get the velocity, isn't it? Is that right? So your v will be, make sure you do the square root, you know the velocity. Now the question is, you are not allowed to do this way. You find this velocity, v, this vy whatever, using energy method. Are you with me? Are you with me? Now what you do is, okay, you cannot use this formula now. But what you need to do here, what you know here is, the formula is what? You don't have any W other. Your formula is K1 plus U1 equals to K2 plus U2. Is that right? Is that right? So here, what is your K1? 0. What is your U1? Mg times 5, right? Is that right? Are you all with me? What about here? What is your K1? 1/2 mvy square is what we want. What is your U1? Oops, U2, K2 and U2, right? Is the second. It will be 0, not almost 0, it is 0. Right? So now K1 is what? 0 plus this one is, and what is your mass? You don't need mass, by the way, this will cancel anyway. Gravity is 9.8, right? Distance is 5, is that right? Equals to, what is your K2? K2 is 1/2 mass. I need the velocity, which I don't know, okay. And what is U2? Which is 0. Are you guys with me so far? Are you guys with me so far? So now when you do this, your m will cancel, right? No matter what is the mass, it will cancel. So here what happens is 2 multiplies this side. So multiply both sides by 2. 2 times 9.8 times 5 equals to Vy square. Are you following? Is that the same thing? Look here. 2 9.8 times 5, whatever you get with the square root, same thing. Did you get the same answer here and there? Does it make sense? Look at here. Here is what? Your V equals to whatever it is, V square root of this guy, right? Here, this guy and this guy is the same thing. 2 9.85, 2 9.85. Exactly the same thing. So whether you look this way or this way, your velocity is the same thing. So that Arthur's machine proves that it's all the same thing. Are you following? That's the same thing. All you do is get the kinetic energy, get the potential energy on the both points. All you do is, this is the only formula you have. K1 U1 plus K2 U2 equals to, sorry, K1 U1 equals to K2 U2. There will be W other also, but W other is, in this case, it is 0. So now, that's what I was trying to do in the gravitation now. If you want to find the escape velocity, hold on, we have 3 minutes. Why are you rushing? Hold on, calm down. So now, let me go back. I use a red pen. What I'm doing here is, I have something here, at the earth here, tiny earth now, okay? Because I don't have more space, so I made it smaller. So mass of the earth here, I throw it with the velocity at this point, alright? I throw it with the velocity what? V escape. Alright? And then it reaches where? Reaches outside, reaches to the infinity. Are you following? At infinity, what will be its velocity? The velocity will be 0, right? So basically your K1, what is your K1 in this case? 1/2 of mv escape square, right? Is that right? Are you all following with me? What is U1 at this point? No. U1. In place of R, you have R of E, right? Radius of the earth, isn't it? So, minus G m mass of the earth divided by radius of the earth square. Are you following so far? Are you following? What will be K2 at this height? Which is 0, because velocity is 0, right? Make sense? What is U2? The potential energy at the end. What happens to U2? Because it's 0. There is no gravity there, right? So K2 is 0, U2 is also 0. So what it means is K1 plus U1 equals to K2 plus U2 When you add these two, 1/2 mv square equals to, sorry, minus gmme divided by re square, so equals to 0. So what it means is your m and m cancels, your 2 will be there, so v square equals to 2gme divided by, what is it, re square. Okay, anyway, so this will be v equals to square root of, just find out, just calculate the remaining thing, okay? And then if you have further question, let me know. If not, I'll see you next week. I hope